Time to do some math. Take it to the hospital. L'Hopital. So what's L'Hopital's rule is a way of evaluating limits that start out as indeterminate forms. What does that mean? So it means limits of the form when you're starting out with, like if you plug in the limit as x approaches whatever, if you start out with 0 over 0 or infinity over infinity, you are ready to go with L'Hopital's rule. That's like L'Hopital type 1. You just go ahead, take the derivative of the top and bottom, not the quotient rule, and throw it down. And if you get 0 over 0 again, you just do L'Hopital again and hope for the best. L'Hopital type 2 is when you have 0 times infinity and you flip one of them over and turn it into one of these. And then L'Hopital type 3 is where you start out with 1 to the infinity or infinity to the 0. No, not infinity to the 0. That doesn't work. What is the other one? The other one is, well, we'll see. We'll update this. Let's get this. Maybe 0 to the infinity. Yeah, 0. Sorry, it's 0 to the infinity. No. Well, we'll see. That might be wrong. You have it in your notes. So in that, you would turn into this by introducing a logarithm and go in that way. All right, so let's do these problems, and we'll see if we can fix that up. Or you probably know from your notes what we should have here. I know what it is. It's infinity to the, no, infinity to the 1? Infinity to the 0. That's what it is. All right, sorry about that. Okay, so number 5. Let's see. I'm not even on the right page in the book here, but I bet I can find it. Number 5. I have the limit as x approaches 0, e to the x minus 1 over sine x. So that's like in this kind of form, but just want to make sure at the start that it is a L'Hopital problem. So plugging in the 0, e to the 0, that's 1 minus 1 over sine of 0. So it is a 0 over 0, so that means I can use L'Hopital. So I just take the derivative of the top and the derivative of the bottom, and then I try again. So when I plug in 0 here, e to the 0 is 1, so I definitely don't have any more work to do. As soon as you get something that's not a 0, then you know you're going to be done. And cosine of 0 is 1, so that's just 1. All right, that's how you do it. Number 7, we know from chapter 2 that, oops, that should be a theta. We know from chapter 2 that this is 1, but we can do it using L'Hopital's rule also. Derivative of tangent, oh, do we get 0 over 0 to start? Yes, we do. Secant squared theta over 1. And secant squared of 0, that's 1 over cosine of 0, and cosine of 0 is 1, so that's just 1. All right. How about the limit as x approaches pi from the positive side, sine x over x minus pi? All right. Is that 0 over 0? It is. So I do the derivatives. And I plug in pi. The cosine of pi is negative 1. All right. How about the limit as x approaches positive infinity of the natural log of x over x? let's see, the natural log of infinity is infinity over infinity, so it is that type. And the derivative of natural log x is 1 over x, over the derivative of that is 1, so 1 over infinity, that's going to 0. Isn't this fun and easy? How about the limit as x approaches 0 from the positive side, cotangent x over natural log x. Alright, well, let's see. What's going on with cotangent function at 0? I do believe that cotangent has a vertical asymptote there, so that's approaching positive infinity, and as you approach here, so this is positive infinity over negative infinity. That's a version of that, so I can use L'Hopital. Derivative of cotangent is negative cosecant squared, and derivative of natural log x is 1 over x. Now 1 over x, if you're dividing by 1 over x, that's the same as multiplying by x, so I'll write it like that. So let's see what we have here. The cosecant squared of x, the cosecant of 0, that's the same as 1 over the sine of 0, and the sine of 0 is 0. So this is a 1 over 0 kind of situation, which is infinity times 0. So that actually got us kind of more into the weeds there. That got us to one of these situations. So what do you do from there? That means it's still indeterminate. We still don't know what the answer is. So that means I have to go from something that's in this form now to this. But this one's kind of well suited for doing that easily because cosecant is 1 over sine. So this is the same as this. So let's see what we can do. I'll just make that minus sign belong with this, so I'll say the derivative of the top is negative 1. That doesn't have any variables in it, so I'm definitely going to be done at this stage, whatever happens. And the derivative of sine squared, derivative of anything squared, is 2 times that thing to the first times the derivative of what's inside. And that is still going to have a 0 on the bottom, so I have negative 1 over 0. So it does not exist. So I would say that one was the trickiest so far. All right. You ever hear the song, like a road trip song, when you've got a lot of time to pass? 99 bottles of beer on the wall, 99 bottles of beer. Or I guess beer is not high school appropriate, so 99 bottles of, let's see, Coke on the wall, 99 bottles of soda, take one down, pass it around, 98 bottles, and then you just keep going until all the bottles are gone. Well, this problem is kind of like that because when we do this, we're like, okay, if I plug in infinity, yeah, I get infinity over infinity, so we're good for L'Hopital's rule. And then I do it again, and I get, let's see, 100. Okay, I'm kind of tired of this game already, and we haven't got very far. It's still infinity over infinity. So let's think here. What is going to happen? If I keep doing this, then I think it's pretty easy to see what's going on here. I'm going to get a 98, and then a 97, and then so on and so on. And I'm going to keep taking derivatives. I'm going to keep getting infinity over infinity. This is going to keep being the derivative of itself. But eventually, after I take 100 derivatives, I'm going to run out of x to the whatever, and it's finally just going to be a number. And if I do that a whole bunch more times, eventually I'm going to get the limit as x approaches positive infinity over 100. How do you write 100 times 99 times 98 all the way down? Oh, that's what factorial is, right? What's our shorthand for that? So e to the x, that's still e to the x. So however impossibly large this number is, and it is impossibly large, that number, for example, is too big for the tiny little brain of your calculator to manage. The biggest number that your calculator can handle is, let's see if it'll let me do this. If you do 10 to the 100, I think that busts it. Yep. But if you do 9.99999 times 10 to the 99th, oops, it's good. So this is that's the cap. 1 followed by 100 zeros, which actually that number has a name. That's a googol. That is the cap for numbers that your calculator can handle. Do you know what 100 factorial is? Oh, it's bigger than that. So it's a very large number. 100 factorial. I mean, 100 is not a very big number, so you just put that little factorial sign after it. And yeah, that's a big number. So I think maybe, let's see, 68 factorial. I don't remember what is the biggest one that your calculator can handle. So that one's good, and then I guess I could just do times 69. Maybe 69 factorial is the biggest one, times 70. Boom! So there you go. So however impossibly large this number is, we're still dividing. It's still just a number. So this is done. It's a number over infinity, so that's going to 0. All right. That was fun. What about the limit as x approaches 0, sine inverse 2x over x? Make sure this is L'Hopital. The sine inverse of 0 is 0, and that's 0. Okay, so we're good. It's L'Hopital. They're not throwing any tricks at us in that way. The derivative of sine inverse is 1 over the square root of 1 minus that thing squared times the derivative of what's inside. Right? A little practice from our section 4.3 stuff over 1. Okay, so now if I plug 0 into this, oh, looks like I just get 2. Number 21. Oops, I think I skipped 19, didn't I? Or I tried to skip 19. X times e to the negative x. So that is of the form infinity times 0, because e to the negative x is the same as 1 over e to the x. 1 over e to the infinity, that's going to go to 0. So what I need to do, this is a real easy one to rewrite in what we're going to call L'Hopitalable form. That's what we would, L'Hopitalable in French if you want. So I'm just going to rewrite that like this. You need to have things in like something over something. It has to be in that form before you can do L'Hopital's rule. L'Hopital's rule always involves taking the derivative of the top, taking the derivative of the bottom, and then trying again. So it must be in that form. And then here I still have, it looks like, well, of course, I just rewrote that. So infinity over infinity now. So I can do my L'Hopital's rule and get 1 over e to the x, and that's going to go to 0. How about the limit as x approaches infinity of x times the sine of pi over x. Well, this is going to be infinity times, and that's going to be 0 and sine of 0 is 0. So it's infinity times 0, so I need to make it L'Hopitalable. So one of these I need to flip over and move to the bottom. And it's always almost the case. It's almost always the case that the thing that you want to move is the thing that's just like a little algebraic expression, like here the x. If you try to move that to the bottom and flip it over, well, I guess that would be like a cosecant on the bottom, and maybe it'll work out that way, but I think probably it's just going to get more messy for you if you do it that way. So I'm going to flip that over, which means like an x on the top is the same as a 1 over x on the bottom. Seems like a weird thing to do. You're taking something that's kind of like, simplified, I guess you could say, and you're making it less simple. But we have to do that because this is not L'Hopitalable form, and this is. So let's see what happens. Now I'm going to execute L'Hopital's rule. The derivative of sine of whatever is cosine of whatever times the derivative of what's inside. The derivative of pi over x is pi times negative x to the negative 2. And the derivative of 1 over x is negative x to the negative 2. So those, it always is the case that when you do something like this and you want to simplify, if you have any x's hanging around in the top and the bottom, you want to go ahead and simplify before you try to plug this in. That is always true. Not always, almost. It's really always. So let's see. As x approaches infinity, pi over infinity is going to go to 0. Cosine of 0 is 1 times pi is pi, and those canceled out. We got ourselves an answer. All right. How about the limit as x approaches pi over 2 from below of secant 3x cosine 5x. Well, secant is the same as 1 over cosine, so I'm just going to go ahead and not even write out an extra step there. That's that. Now, is it true, let's see, is the cosine of 5 pi over 2, is that 0? Yeah, cosine of any multiple of half a pi is 0. So I think we're L'Hopitalable here. So what's the derivative of cosine of 5x? Derivative of cosine of whatever is negative sine of whatever times the derivative of what's inside. And let's see, the sine of 5 pi over 2 is the same as the sine of pi over 2, which is 1. And the sine of 3 pi over 2 is negative 1. So I think negative 5/3. I don't know why I made that line there. I was going to sketch the sine function, but I just decided to use my imagination instead. Okay, and these last two are L'Hopital type 3. These are the toughest ones. So what we're going to do is, here, I'm going to scribble that out. First we're going to scribble, and then after we do step 0, which is scribbling, then we're going to say, let's let L equal the limit that we're trying to find. So let's see, the limit as x approaches infinity of 1 minus 3 over x to the x. Okay, so why did I do this? Because I would like to get this down. What I need to do is I need to get from this well, actually, real quick, let's just plug this in. If I plug infinity in here, 3 over infinity, 0, I have 1 to the infinity. That's one of the forms that I need to like work back through this. So I need to get from this form back to this by getting the exponent down, and then back to this. How do you get an exponent down? That's what logarithms are for. So the natural log of the limit of whatever the answer that I'm looking for is equal to, if I introduce a natural log here, I'm going to put it on the inside. Oops. Sorry, I didn't mean to leave that space there. I'm going to move that x out, because if I insert the natural logarithm here, then one of my rules that we used in logarithmic differentiation, right, is to get this exponent down to the front. So I can do this. And that should turn it into, if I plug in infinity now, infinity times the natural log of 1, which is 0. So it turns it into an infinity times 0. Okay, so that means I've got it from L'Hopital type 3 to L'Hopital type 2, and now I need to pick one of those two things and flip them over. And I'll tell you what is definitely always almost true. In fact, it's always, always true, is that you want to flip this over, not the thing, not the logarithm. That would just get really, really insanely yucky and ungood for you. Oh, they're going to do the announcements right now. Hold on a wee second.
Today is Thursday, October 29th. Please join me for a moment of silent reflection.
I'm coming back. Here I come. All right. So, I'm going to leave this on top, natural log of 1 minus 3 over x. And then here on the bottom, 1 over x, or you could write it as x to the negative 1. A little bit more calculus friendly. You could rewrite that too, I guess, if you want. And now I can do L'Hopital. Now if you plug in the infinity, it's the natural log of 1, which is 0, over infinity upside down, which is 0. Okay, so let's see. Limit as x approaches infinity. The derivative of this, derivative of natural log of whatever, is 1 over whatever, times the derivative of what's inside. That's negative 3 times, and then the 1 over x is negative x to the negative 2. So I guess you could cancel out those negative signs if you want. And probably that would have been easier if we had written that or rewritten that as 1 minus 3x to the negative 1. That would have been a little more evident. And then x to the negative 1, that's negative x to the negative 2. Okay, so the x to the negative 2's cancel out, but you got to be careful, this negative sign is going to hang around. So I still have a negative 1 here after I cancel those. And then, when I plug in infinity, I get 1 over 1 minus 0, that's 1, and that's 3, and this is negative 1. So I get negative 3 there. And is that the answer? Almost. Natural log of what we're looking for. We're looking for L, right? Whatever L is. The natural log of L is equal to negative 3, which means L is equal to e to the negative 3. That's the answer. And that's what L'Hopital type 3 feels like. Let's see if I can fit number 27 in here and not use another feuille de papier. That's French for a piece of paper, but it's not a piece of paper. In French, it's a leaf of paper, which is nice, I think. E to the x plus x to the 1 over x. So quick check, we're going to 0 here, so that is 0 to the infinity, and that is the, oh, is that the other kind that we thought? Oh, no, sorry, it's 1 to the infinity. Yeah, e to the 0. So it is that other kind, that other form. Let's see what we can do. So that's going to be equal to, let's let that equal L. So the natural log of L is equal to the limit, and I'm going to do the natural log thing, which is going to bring this down, 1 over x times natural log of e to the x plus x. And this one, this is kind of nice because because this was a 1 over x, it kind of automatically wants to get into that L'Hopital type 1 form. If you plug in the 0 here, you do get infinity times the natural log of 1, which is 0. Yeah. You do get infinity times 0, but this automatically kind of wants to go, or very naturally, not automatic, that's the wrong word, wants to go to the bottom because it's already 1 over x. So I hardly need to rewrite that. I mean, it's just same as that, right? Okay, so now I can do L'Hopital's rule. And get, let's see, the derivative of natural log of whatever is 1 over whatever times the derivative of what's inside. Right, that's the derivative. That's 1 over this. And then I left that blank, so when I do the derivative of what's inside, I could write it up there. Over the derivative of the bottom, which is just 1. And if I plug in my 0 now, I get e to the 0, which is 1 plus 1, over e to the 0, which is 1 plus 0. So that's 2 over 1, 2. So my answer, my limit that I'm looking for, that's the natural log of the answer. So the answer is e squared. I'm just going to flip to the back of the book and check those real quick and make sure I didn't tell you anything that's not true. If I did, we'll go back and fix. So let's see. Starting with number 5. You already know if these are right or not because you probably already checked, but I just want to make sure. So you got 1, 1, negative 1, 0. They put negative infinity here, whatever. Does not exist is fine. 15 is 0, 2. 19 is 0, and then pi, negative 5/3, e to the negative 3, and e squared. Yay!